Okay, good morning everybody. Thank you, Andy, for bringing together this nice workshop again on retinal oximetry. And what I try to do is to show you that oximetry, which you all may know is good, but doing oximetry combined with flicker stimulation can give us more information. And you all know, and Gerhard already have shown it to you, that flicker stimulation results in so-called neurovascular coupling, and by that we see an increase of the retinal, arterial and venous diameters during the flicker, and this shows us an increase of the blood flow, since the total blood volume flow per unit of time is related to the fourth power of the radius of the vessel. So that also is a slide you know from Gerhard's talk, so I can be brief here. Neurovascular coupling is a complicated mechanism, basically triggered by glutamate, which binds to the NMDA receptor in the neurons and to the glutamate receptor in the glial cells, and then regulate the vessel diameter via the NO, but also via arachidonic acid and prostaglandins and so on. That is stuff I think Gerhard knows better than me, so that's I will briefly skip here to the next. That is also something you know. We get an increase of the oxygen saturation in the veins by about 5% during the flicker. The response is not that fast. Then the diameter response, we need about 90 seconds to reach steady state, versus about 20 seconds with the diameter, but basically we get this increase. And now what is our idea about the mechanisms? The oxygen, of course, is supplied by the vascular system, but is consumed in the tissue. That's why it has to go there via diffusion. That needs a diffusion gradient, a concentration gradient from the vessels to the tissue. And if we now apply the flicker, we increase our oxygen consumption by neuronal activity. Thus, we have to increase the diffusion in order to supply sufficient oxygen. And if we want to do that upon constant PO2 in the tissue, we have to increase the PO2 in the vascular system. This is done by the vasodilation, and as the PO2 is related to the oxygen saturation by the oxygen binding curve of the hemoglobin, we finally measure this increase of oxygen, of hemoglobin oxygenation in the veins. Well, now it is a debate whether this is now hyperperfusion or whether this is just meeting the needs of our tissue. Well, Gerhard just told us that possibly the oxygen consumption is not the only or not the main force driving the neurovascular coupling. So this is still under debate, but this is just a simple, maybe a little bit mechanistic model. And now I'd like to give you a short overview on clinical experimental studies we did. First, the methodology, we measured the oxygen saturation in this standardized area here, known from the RX study, and we average overall the oxygenation values from all vessel segments, arterial and venous vessel segments within this ring. Furthermore, we measure the diameters and calculated the central arterial and venous diameter equivalent according to the formula given by Parr and modified by Hubbard. And Then, after we have done the baseline measurement, we apply the flicker for 90 seconds with a frequency of 12.5 Hertz, and do the measurement once more during the flicker. So now some results. We did a study of retinopathy. This is a survey of our patients. We had 19 diabetic patients and 20 controls of same age, same blood pressure. However, the weight and the body mass index of the patients was higher than that of the controls. Patients had mostly type 2 diabetes, but we also had 4 patients with type 1 diabetes. Duration of diabetes was on average 24 years, and the HbA1c was at 7.7%. So what did we find? First, we looked at the vasodilation, and we found, so where is my mouse cursor? We found an increase here of the arterial and venous diameters in the control group. However, no significant increase in the patients. And looking at saturation, we found increase of the venous oxygen saturation by the flicker in the controls, as I showed it before in another young control cohort. But the increase of the venous oxygen saturation in the diabetic patients was still significantly less than in the controls, with 2% versus 4.2%. So we found a correlation between the arterial vasodilation and the venous oxygen saturation change. That means that subjects who showed still a good reaction of the arterial diameter to the flicker also showed a reasonable increase of the venous oxygen saturation, while the patients with a low reaction of diameter also showed a low change of venous oxygen saturation. And furthermore, we found a trend which was not significant, but clearly a trend of lower reaction of the venous oxygen saturation with higher body mass index. So what is the idea? Maybe this feedback loop between oxygen consumption and the vasodilation is somehow impaired in the diabetic patients, resulting in an insufficient increase of oxygen supply upon the flicker, and finally this may result in hypoxia in the retinal tissue, which might be a reason for neovascularization in proliferative diabetic retinopathy. So next study we did in glaucoma. Here again is the survey of the patients. We had 41 patients and 40 controls, again with same age and same blood pressure. However, the retinal nerve fiber layer and the rim area measured by OCT was significantly lower in the patient group. We also graded the glaucoma according to the glaucoma staging system 2, published by Brusini. This is based on visual field measurements. First the generalized defect and also the localized defect, and then we get 7 stages, but we grouped them in order to have enough subjects in each group to mild, moderate, and advanced glaucoma. And what we found was again a decreased flicker response with respect to the diameter, especially in the veins, but also a decreased change of the venous oxygen saturation, as well as the arterial venous difference. And upon subgroup analysis, we saw that at baseline the oxygen saturation was lower or decreased with the severity of the disease, and furthermore the change of the arterio-venous oxygen saturation shown shown here in the right part also decreased with the severity of the disease. You have to keep in mind that these are negative values, so that's why it looks like an increase, but in fact it is a decrease of the AV difference change. So what is the idea? Well, a very simple idea. Because of the dropout of the nerve fiber layers of tissue, we have a reduced oxygen consumption, and that's why possibly we don't need so much oxygen anymore, and the response to the flicker is also lower. But if this is the case, we should have an correlation between the flicker response and the retinal nerve fiber layer thickness, and we changed for that, and there was a slight trend, but there was no significant correlation. And even if we looked at only the retinal quadrants with nerve fiber layer below the first percentile of the normative data of the OCT device, and compared that with the rest of the quadrants, retinal quadrants, there was no significant difference. So that we have to question this hypothesis that the dropout of neurons is responsible for these findings in oxygen saturation. Furthermore, in order to test that in detail, we have a study underway. This is data from an ongoing study where we compare the oxygen saturation of the vessels supplying a scotoma area and compare that with the vessels supplying non-scotoma area. That means here we included only subjects with a localized visual field defect. Up to now we have 11 subjects in the study, and you see that there is virtually no change of the venous oxygen saturation by the flicker in the non-scotoma area, but in the area of the scotoma we have about 3% increase of the venous oxygen saturation, and more more clear it gets if we compare the AV differences. Here the decrease of the AV difference in the scotoma area is about 4%, and that was statistically significant compared to the zero baselines to no change. So that's a little bit striking, since if we look at the non-scotoma area, we might argue that, well, this non-existent response of the AV difference to the flicker here points to a primary effect. That means this may point to the to that it may be a reason for the glaucoma development, that we have a dysregulation of the blood flow and oxygen supply. But if we look at the scotoma area, we have no good idea up to now why this looks more physiological than in the non-scotoma area. So, as we have a lot of glaucoma experts here, maybe one of you have an idea what might have happened here. Up to now, I don't have an explanation, I have to admit. So, well, this all that data hint to the fact that dysregulation of blood flow may be contribute to the development of glaucoma. So the question is, do we have hypoxia in the glaucoma? I don't believe that we have permanent hypoxia, but it is known that periods of hypoxia and repeat perfusion injury may contribute to neuronal loss via oxidative stress in the neurons. So the last study we did in age-related macular degeneration patients, briefly, we had 46 patients and 23 controls, again age-matched, and if we compare them, there was no difference in the arterio-venous difference of the oxygen saturation between the controls and the patients. However, at the change of the AV difference by the flicker, we found again a physiological reaction in the controls, but significantly reduced reaction in the patients. And subgroup analysis revealed that there was a statistically significant difference for all groups except the neurovascular AMD. So, well, in conclusion, we might state that flicker-induced change of the retinal vascular oxygen saturation, along with the measurement of the vasodilation, indicates impairment of blood flow regulation in order to address the needs of oxygen better than just oximetry, or to sum it up in a very simple take-home message, oximetry is good, combination with flicker is better. Thank you for your attention.